Hello friends, in this video I'd like to solve the following problem from the Indian Olympiad Qualifier in Mathematics 2023/2024, problem 23. It is actually a problem suggested by one of my viewers, for which why I am very grateful. So the problem states, let A be point 1284 and I be 0, 0. Find the number of right triangles ABC with right angle at vertex A, whose vertices B and C are lattice points, meaning that they have two integer coordinates, and whose incentre is point I, 0, 0. It's a very nice problem combining linear algebra and number theory, as you will see in a moment. So here are my hints. First, without loss of generality, you may assume that ABC is oriented anti-clockwise, and you should be able to find the points at which the incircle touches lines CA and AB, and call these points M and N respectively. Notice that points B and C can be written as B equals point A translated by a vector am multiplied by some number, and C can be written as point A translated by vector an multiplied by some number, which two numbers m and n are real numbers, positive real numbers. And then, the funny part, try to form some kind of Diophantine equation and count the number of its solutions. Also, make a good drawing, that is very helpful, and also remember this fact that if we have two vectors, xy and y minus x, then these two vectors are perpendicular because of properties of dot product, for example. So give this problem a try, and I will see you in just a minute. Alright, so here I have made a drawing on which some points are already marked, but we'll cover all of it. So first, notice that point I is given to us. I is 0, 0, and A is given to us. It's 1284. So point B lies somewhere here. Point C lies somewhere along this line. All right. First of all, I wish to find points at which our incircle touches these two sides of our triangle. How can we do it? Well, let's take a look. First, notice that that a square is formed by point A, points M and N, and by the incentre, because here we have a right angle. So here we also have right angles, and here also, and these two sides are equal because they are just radii of our incircle, so we have a square formed. First, let's find the midpoint of this square. How can we find it? Well, it's just the arithmetic mean of A and I. So point P can be found by adding A and I together and dividing by 2, and that happens to be 6. 6, and the second coordinate is 42. 42 is this point. 6, 42. All right. Well, how can we find M and N? What's the easiest way? Well, probably the easiest way is to consider vector IP, and notice that to reach points M and N, we should go along the perpendicular vector of the same length. So notice that vector IP is also 642. I do not distinguish the notation. I do not distinguish points and vectors. I will write them both in normal parentheses. All right, and now notice that point M, we can go ahead to point M by taking point P and traveling along the vector perpendicular to IP of the same length. And vector perpendicular to IP of the same length, and we also notice that we go to the right, so the first coordinate should be positive. So we need just to add 42 minus 6. So you are adding 6, 42 plus 42 minus 6, which is 48, 48, 36. 48, 36. And let's mark it. 48, 36. And how can we find the point n? Well, the same thing, but we go in the other direction. So n equals p minus 42 minus 6, which is 6, 42 minus 42 minus 6, which is minus 36, 48. Yes, minus 36, 48. And our drawing seems to confirm it, because here we have somewhere 48, 36, probably right. All right, now let's take a look. Let's find vectors am and an. Well, vector am, a is, so we just subtract point m from point A, and to find an, we subtract n minus a, and we will find that this first vector, am, is 36 minus 48, and the second vector is minus 48 minus 36, and also let's notice that they are both, it's 12, 12, 3 minus 4, minus 4 minus 3. All right. Going along these vectors, we'll eventually reach our points. So we can write that point point B can be written as point A times some multiple of this number. Let's maybe call it m. B equals m times, let's take a look. B is here, so we are going along vector an. So it's m minus 4 minus 3, and C is a plus some number n times 3 minus 4, where I'm just stating that they are positive. Because if you look at the drawing, we are going in the right direction. This vector has two negative coordinates, and this vector has first coordinate positive, the second one negative. So we have positive scalars in front of these vectors. All right. So in other words, our points B and C can be written, B and C, B is 12 minus 4m, 84 minus 3m, and C is 12 plus 3n, 84 minus 4n probably. All right, and now notice the following thing, that points B and C are lattice points, so they have two integer coordinates. So B and C are lattice points. So we can deduce the following. So if I write, for example, I can write xb, the first coordinate of point B, I can write it as 12 minus 4m, and yb can be written as 84 minus 3 times m. And after subtracting these equations, we get that m, or maybe xb minus yb equals minus 72 minus 4m plus 3m. So it's minus m, which says that our number m should be a positive integer. It must be a positive integer. It's not just some positive real number. It's a positive integer. And the other way around, if m is a positive integer, then b is a lattice point. It's a lattice point, obviously, because here we have just coordinates. And similarly, you can check it yourself. C is a lattice point if and only if and only if this number n is a positive integer, given that these points are positive numbers. All right, very well. Now let me write our points once again. Points A, B, C. So point A is 1284. Point B is 12 minus, let's go back, minus 4m. 84 minus 3 times m. And the last point is this point, where m and n are some positive integers. All right, now let's find the length of sides of our triangle. So BC, the length of this segment, pretty easy to verify. It can be written as 5 times m squared n squared square root. Moreover, CA can be written as 5 times n CA. Yes, and finally AB can be written as 5m. All right. Now, what else do I wish to do? Well, to go onwards, I wish also to find the inradius of our incircle. How can we find the inradius? Well, we can find the inradius by just computing the length of segment IM, for example. IM. So IM inradius. The inradius of triangle ABC, it's R, and it's just the length of segment IM, and this happens to be square root of coordinates of point M. I don't remember these coordinates, so I will look back. 48, 36. 48, 36. 48 squared, 36 squared, which happens to be 60. And now I will use a well-known formula for the inradius of right triangle, namely, if I have a right triangle with sides, let's see, A, B, C, right angle at vertex A, B, C, A, and I have inradius, incircle, and inradius R, there is a well-known formula that it is C or B plus C minus A over 2. All right, and now, so I wish to solve the following equation. 60 equals the length of one segment 5m plus the length of the other segment minus the length of a hypotenuse. Over what? Over 2. All right. And now we can simplify it. It's 24 equals m plus n minus m squared plus n squared. And now we just want to find the number of positive integers which satisfy this equation. And this will be the number of these right triangles which we seek. So we wish to find the number of pairs mn positive integers satisfying this Diophantine equation. How can we do it? Well, let's do the following. It's m squared plus n squared equals m plus n minus 24, and we have two cases. If the right hand side is negative, then we have no solutions. When it isn't, we can raise both sides to the second power. We have two cases. Maybe let's write them. Case number one, if m plus n minus 24 is less than 0, then we have no solutions. Case number 2, interesting for us. Let m plus n be greater than or equal 24. Then we can do the following. We can raise both sides to the second power, so we have m squared plus n squared equals m plus n minus 24 squared. And let's expand it. We have m squared n squared plus 576 plus 2m n minus 48m minus 48n, which after simplifications we can write it in the following way: 0, because notice that this and that cancels with these terms, we can divide by 2, and we'll have mn plus 288 minus 24m minus 24n equals 0. Now, since this is a Diophantine equation, I wish to write something the right hand side as a product. How can we do it? Well, notice that I can write m minus 24, m minus 24, and I have n should be here, and I have mn as I should, I have minus 24m as I should, minus 24n as I should, but I have introduced 576, and I only want to have 288, so I will write 288 on the left hand side, and now it's balanced. Right, and also notice we are getting very close to the solution. Notice that the right hand side, 288, can be factorized in the following manner. It's 2 to the power of 6 times 3 squared. All right. So we are just seeking the divisors, the positive divisors of this number. How many divisors does, 2 to the power of 5, my bad. How many divisors does this number have? Well, notice that 2 to the power of m times 3 squared has 5 plus 1 times 2 plus 1 which equals 18 positive divisors. How do I know it? Well, if you think about it, if we have a prime factor decomposition of a number, every positive divisor is composed of the same primes, but with different exponents. So for example, when constructing a positive divisor, I can take 2 with what power? Well, with power of 0, 1, 2, 3, 4, or 5. 6 options. 6 options. And I can also have number 3 with exponents of 0, 1, or 2. 3 options. So 18 options in total. Alright, so we have 18 positive solutions of our equation. Our equation has exactly 18 different solutions, different pairs of solutions. And also you may wonder, but is this condition satisfied, that m plus n is greater than or equal to 24? Of course it is, because every number is, for example, m is 24 plus a divisor, a positive divisor, so it is greater than or equal to 24. So already m itself is greater than or equal to 24, n is also greater than or equal to 24, so this sum is also greater than or equal to 24. And now we have reached our answer. The answer is 18. There can be constructed 18 non-congruent triangles whose vertices are on the lattice points, whose incentre is 0, 0, whose vertex A is 12, 84, and whose right angle is at the vertex A. So I don't wish to write anymore. The answer is just 18. 18. And moreover, one more thing, you may wonder, is it 18 or maybe twice that? Well, I'm not sure about the interpretation of this task, but I consider, for example, triangle which looks like that. A, B, C, CB. I consider them to be the same triangle with just different labeling of vertices. If you consider these two triangles to be different, then multiply the result which we get by 2, and doesn't really matter. For me, it's 18. And that closes our problem. So yes, it's a very nice problem, I say, very creative. And also, one more thing, as I said, this problem was suggested by one of my viewers, I believe from India. And also, if you wish to suggest a problem which I may solve, then feel free to do it in the comment section or community section. But two things. First of all, I cannot guarantee that your suggestion will be solved, because I have only a finite amount of time to solve math problems. And also, if you suggest any problem, always give me a link to some PDF or to a place where I can find the problem statement, because every time I provide a link in the video description. I like always to give a source for my videos. So yes, that is it. And also, I don't like nothing. Okay, so thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.